All right, thanks to everyone who's stuck it out to the end of this workshop. You're the real troopers. So what I want to do today is I want to sort of take over where Adam's tutorial left off when he was talking about kind of lower bounds in privacy and attacks on kind of allegedly private data releases. And so this is going to be kind of a compilation of a couple joint works with several co-authors who are here, Adam and Cynthia, and also Mark, Salil, and Thomas, who are not. But all of the kind of bias and editorializing and outrageously broad statements are mine, so don't blame them, unless they would like to jump in to save me. So, all right, so like a good story, we'll start with sort of a cast of characters. So what I'm going to do in this talk is I'm going to try to specialize on sort of one very, very specific problem so that we can kind of understand it. And the problem is extremely simple to state, so you don't really need to know very much about differential privacy at all or about any of the algorithms. Everything is very simple. So what is the problem? So there's some population of individuals that you want to study. There are these little cartoon guys in this cloud. And you've randomly sampled individuals from this population to get this nice data set. And what you want to do is you want to learn just some very simple information about the data set. You just want to learn what I'm calling its marginals. Okay, so this is sometimes slightly abusive. These are often called the one-way marginals. I just want to learn the mean of each column, or the row-wise mean of this matrix. Okay, so here the data is binary. I represented it plus minus 1 for kind of technical reasons that are irrelevant for this talk. But you can see the average of this column is 0.5. Okay, and I just want to learn this for every column. All right, and some sort of important notational things for this talk. Sort of n is always going to be the number of people I sampled. And d is always going to be the dimension of this data set, the number of marginals I want to learn. Okay, so this is like an extremely basic problem. Pretty much anything you can ask about a data set is sort of strictly more general than this problem. So it's a good place to start. And the question that I want to ask is how accurately can we release this vector of marginals on this data set while respecting privacy? Yeah, they're going to be binary for this talk. This is not completely fundamental, but makes a lot of things simpler. And I don't think the difference between plus minus 1 and 0, 1 will ever matter. So I say how accurately can we release the marginals of this data set while respecting privacy? And I intentionally left privacy a little bit vague here. So ideally, we would like to have some sort of strong notion of privacy, such as differential privacy. But since this talk is focused more on kind of lower bounds and attacks, certainly at a minimum, what we'd like is to be able to avoid attacks. So certainly, if you're proving lower bounds, it's better if you can prove lower bounds that actually correspond to realistic attacks against sort of a broad class of algorithms rather than specifically proving kind of technical negative results for differential privacy. So this sort of distinction is going to be kind of paramount to the talk. I'm going to talk both about lower bounds for differential privacy, but also to what extent these lower bounds correspond to sort of realistic attacks. So let me just give sort of like a very kind of high level sort of like sort of background. So why do we want to study lower bounds and attacks? So I think sort of the motivation for understanding these attacks is that we want to understand these sort of inherent risks in releasing sensitive personal information. Okay, and this is sort of interesting not just as like a philosophical question, but these sort of attacks tend to actually come before kind of interesting privacy definitions. So these things tend to sort of motivate a lot of the investigation into privacy. So for instance, re-identification attacks, like even things predating the Netflix attack by like 20 years, were sort of very influential in getting computer scientists thinking about these problems and have continued to be. Attacks against sort of aggregated statistics, so things that in contrast to the things like the Netflix attack work on statistical information, have also been influential in practice. There is a sort of well-known attack by Homer et al. Against certain genetic data releases that really sort of motivated this work, and you'll hear more about this attack. But this had a lot of influence on how the NIH releases genetic data. And of course, sort of the kind of reconstruction attacks of Dinur and Nissim, which we've heard about many times, in many ways inspired the work on differential privacy. So we want to understand attacks as a way of kind of motivating our inquiry into designing good private algorithms. And of course, just you know, as sort of theoreticians, which most people in the audience are, we want to understand optimal algorithms for a given definition. So in many cases, these reconstruction attacks like Dinur-Nissim sort of already gave optimal lower bounds for differential privacy before there even was a differential privacy. But in the case of the problem we're going to study today, is a case where there was a big gap, and so we want to understand new techniques for sort of plugging this gap and getting optimal lower bounds for differential privacy. Okay, and so what I'm going to do today is I'm going to talk about an attack that I guess I like to call the fingerprinting attack. It goes by many names, but you'll see why. And how it is important for establishing kind of a price of differential privacy in these high-dimensional data sets. So in settings where D, the parameter I defined, is quite large. And as I said, I'm going to do this by giving like a very detailed case study of just like one problem, just this one problem of releasing the marginals. But I claim that it captures like many of the interesting phenomena that arise in differential privacy. And you know, my evidence of that is that there have been many papers using sort of this problem as like a hub for hardness in many other problems, including some not even in differential privacy. And hopefully there'll also be a lot of questions from the audience. You know, it's like the second to last talk, so I'd rather have a discussion than talk at you. Oh, it's pronounced Smith, actually. It's, yeah, English is a funny language. Okay, so thank you. Great example of a question from the audience. Amos is participating. But I will not give any kind of broad coverage, and I'll give like proof sketches, but I'm going to try to have like, I'm going to try to be sort of vague about exact proofs. I want to make this more about sort of the models and the results than about the technical arguments, but give you sort of enough that you could kind of go look at the papers if you're curious. All right. So as I said, stop me anytime for questions or comments. So let's kind of return to this problem of releasing the marginals of a data set in just a minute. So before we do, I said, you know, the question is how accurately can we release the marginals? So I want to just go over something really quick to sort of set expectations for like what is accurate, like what is a good measure of accuracy. So remember I said that I want to think of the marginals as coming from like this population. Okay, so I have this data set. The population is just a fiction, but like I want to think of it as coming from a population. So there's already some noise from sampling like inherently in the marginals of my data set. Okay, there's some unavoidable noise from randomness. So how much noise does the data already contain? Well, kind of a standard argument in pretty much every field says that basically these marginals, the sample's marginals, will be kind of close pointwise to the population marginals. We're closest to within about 1 over square root of n, where remember n is the number of samples. Right? I'm intentionally, yeah?
So is the assumption here that the sample size is smaller than the data size? So
what?
You're sampling, if the alphabet size of the underlying.
So I'm saying, so there's a d, which I've like intentionally suppressed. It depends a little bit on what you want by close. So if you want that like a random entry in this vector will be close to a random entry, you know, the corresponding entry in this vector, then the average distance will be 1 over root n and independent of d. If you want a stronger guarantee that like every entry in this vector is close to every entry in that vector, then you'd have to take like a union bound and you'd put like a log d here, or root log d or something like that. Okay, so I'm intentionally suppressing d, but the point is that it's going to be small, and you'll see it'll be much smaller than the noise that comes in for privacy in a minute. Okay, so the question is sort of, we want accuracy, but really like sort of the dream, in some sense getting like perfect accuracy is almost irrelevant. Like the dream is really just to get better than 1 over square root n accuracy. Because if we had that, then we would be able to say that the error for privacy is like dominated by the error we already have in our data set. Okay, so let's see, like, is this possible? Like, what accuracy can we get from differential privacy? And like, what I'm going to do is, you know, we're talking about high-dimensional data, so I want to do like dimensionality reduction. I'm going to project all of differential privacy to this line, and the line, now we go from less accurate to more accurate, and let's start kind of filling in some points on this spectrum. Okay, so if you were at Adam's tutorial or many of the other differential privacy talks, you should have at least like a general sense of how one would release marginals with differential privacy, but I'll review it just to sort of set the parameters and the normalization. So let's suppose I have one marginal. So it's this is like let's make this a genetic data set. This is whether you do or don't have the ZBTB7 gene, which funny story was once called the Pokemon gene until Pokemon threatened legal action. Fair use, I say, but whatever. It's a terrible gene. You don't want it. So anyway. So anyway, so you have this data set. Okay, the exact marginal is 0.5. So how am I going to get differential privacy? I'm going to just take this answer. I'm going to add noise from an appropriate distribution, maybe Laplace, maybe Gaussian. But the standard deviation of the noise will be about 1 over n. Okay, I'm deliberately suppressing the actual privacy parameters. They're not so relevant for this talk. But in terms of n and d, which are the only parameters we care about, the accuracy is about 1 over n. Okay, so I get this differentially private answer. And this is great, right? So I've added noise 1 over n. This is vanishing faster than the noise already in my data set, at least in some reasonable range of parameters. So in some sense, for one marginal, like everything is good. If you're in this kind of low-dimensional world, privacy almost comes for free. All right, so what if we have a high-dimensional data set? So what if we measure many genes and whether you do or don't have that gene? So the composition theorem for differential privacy, or you can give a direct analysis, says that in order to get privacy for this whole vector, it's sufficient to add noise independently to each entry of the vector, where the standard deviation will be proportional to the square root of d over n. Okay, so this basically says if I want to sort of treat these each as d separate differentially private algorithms, I have to like clamp down my epsilon by a factor of 1 over root d. Okay, so this is one algorithm. It adds noise to each entry about root d over n. Okay, and this is still good. It's still the case that as n is going to infinity, the error is going down pretty quickly. And in fact, as long as n is bigger than about square root of the dimension, I get some kind of non-trivial error. When I say non-trivial, I'm talking about the fact that these answers range from like -1 to 1. So if I have error bigger than 1, I'm really getting nothing. Okay, so this is like sort of a classic positive result for differential privacy. And if you're in this low-dimensional setting where the dimension is smaller than n, then this root d over n becomes dominated by 1 over square root n. And so in this setting, you could sort of make a case that differential privacy comes for free. Right? And this is a really great thing. We get basically we get this very strong notion of privacy by adding noise that's sort of dominated by the noise that's already in our sample data. Yeah, but of course, in what I'm calling high-dimensional data, where the dimension is much bigger than the number of samples, then this is actually substantially inaccurate. Okay, so it could be non-trivial. There's a wide range of parameters where this is non-trivial error, but it's bigger than the 1 over square root n error that we were really hoping for. Okay, so I'm sort of putting this fairly far off to the left on the less accurate side. Okay, this is a good time to. I went through this a little fast because this is sort of arguably review for many people, but.
Can you still explain and understand why, if you have several samples, why you can just root the n?
So why this?
Yeah.
Okay, so the real bound here is like 1 over epsilon n, where epsilon is my privacy parameter. Okay, so if I treat these as kind of d separate mechanisms, then I can reduce the value of epsilon, and then I can apply the composition theorem for differential privacy. Right, so if I answer each of these with some epsilon differential privacy, then the composition theorem says that this entire process will satisfy some epsilon prime differential privacy. And if you use the tightest results, then epsilon prime will be about epsilon root d. Yeah, so that says I have to sort of clamp down privacy by, clamp down epsilon by like 1 over root d, which means that since the dependence is like kind of 1 over epsilon hidden in here, it gives me a root d over n.
So do you make any assumptions for these marginals?
I'm making no assumptions. So this is just an arbitrary bit, an arbitrary matrix of plus minus ones. I'm making absolutely no assumptions about them.
That's the cost of the delta. That's the cost of
Yes, yes, at the cost of a delta. Yes, so there's a delta also hidden in here. So this is approximate differential privacy. You know, but like the delta can be negligible. So like can be negligible in a formal. It can be negligible in a formal technical sense that cryptographers like. But yes, it is not a completely trivial factor. And Cynthia and Guy's concentrated differential privacy is aimed at giving a meaningful privacy guarantee without that. But for this talk, we're going to just focus on these polynomial factors. Okay, so very upfront, this is like a very theory, kind of high-level description. There'll be a delta, but it's a different delta. Okay, so we're talking about this high-dimensional setting where this algorithm, I'm saying, is non-trivially accurate, but is not as accurate as we'd like. So let's think about whether we can do better. Okay, so Adam, in his tutorial, and you'll see in many talks, like Sal shows, there are many algorithms that give more accurate differentially private output than just the simple additive or independent noise approach. But I claim, and you'll have to trust me on this, that none of them are applicable here. Okay, maybe there's something clever we haven't thought about. So let's think about what we can do to give lower bounds here. So what is an attack we can do with marginals? So let me describe sort of an attack which is sort of from a theoretical perspective very close to something that Adam talked about in his tutorial, these reconstruction attacks. But let me give sort of a very appealing kind of way that this reconstruction attack might arise in practice, which was identified and actually used by Homer et al. Against sort of real data sets. So this is kind of an appealing way of carrying out something like a reconstruction attack. Okay, so again, the models, we have this population, and we have this data set, which was sampled from the population. Okay, so this is the model. And now, here's what I give the attacker. I give the attacker the exact marginals of the data set. Okay, so this is what I want to release to the public. And now the attacker has in mind some target individual that, and what the attacker wants to know is this individual in the data set or not? Okay, so you can think of the data set here as having actual sensitive information. You're in this data set because you are ill and you're in a medical trial, for instance. Okay, and then I'm also going to give the adversary the marginals of the population. Okay, and I wrote exact here. It doesn't really have to be exact, but very accurate. So smaller than 1 over root n. Okay, so these three things are what the attacker has. And what Homer et al. Showed is that if
sorry.
Sure.
How exactly do you get the exact marginals of the
That's the assumption is that the assumption is that someone collected this data set and released these marginals because they thought this is aggregated information, it's safe to release. So I'm not cleverly hacking into any data. I'm just, the NIH decided that they wanted to make this data set available for study. They said, I don't know, this looks pretty safe, let's release the marginals, so now that's public. Okay, so I'm trying to argue why they shouldn't do this, so hopefully you can't get them. Okay, so this is what the attacker has. And what they showed is that under certain assumptions, they can identify whether or not this individual is in the data set. Okay, so just by looking at these marginals and this kind of side information about the population, they can figure out if this string appears in the data set. Okay, and what are these assumptions? So they need the data to be high dimensional. The dimension has to be bigger than n. Okay, well, they need the data of the target individual, and they need this knowledge. Okay, so these are the assumptions. They're fairly mild. And by identify, I mean in a very strong sense. So any individual in this data set, or almost any individual in this data set, they would say, yes, that individual's in the data set. If I took this individual from the population who's not in the data set, they would say, no, this individual is not in the data set. Okay, and this works sort of as long as the population is kind of non-trivially random. Right, so that's a strong assumption. So in their setting, they sort of assume that you get kind of a lot of independent samples. So maybe these are people, these are people just in the world, and you know a lot about people in the world, right? You get lots of random samples. But then this data set is some kind of special person, and maybe you assume that there's not too much kind of correlation between being in the data set. But so yeah, so no, the model is not really that someone releases this vector. I mean, it's sort of an abstraction, but maybe more that you have enough random samples that you can estimate it very accurately. So when I say exact, I'm being imprecise, which is slightly ironic. Yes, so it is important that D is like a random sample of this population. It's important that D is a random sample of this population, or at least like from a very similar population. I may return to this for like a minute at the end. Okay, so I said that you need exact marginals to pull this attack off. I claim that, I sort of claim without proof that in fact it's sufficient for the marginals to be accurate to within much less than 1 over root n. So basically, as long as the error is dominated by the sampling error, I claim that this attack works with slightly relaxed guarantees. Okay, and from a technical standpoint, this is actually really sort of an instantiation of sort of the Ur lower bound in differential privacy due to Dinur Nissim, but I like this story for how it arises, and it's going to be relevant for our results. Okay, so now we've kind of filled in like the two like extreme ends of this like one-dimensional landscape, and we know that sort of we can get this much accuracy, which is not better than the sampling error when D is large. And we also know that you can't get exact accuracy, you can't get perfect accuracy, and you can't get even like nearly perfect accuracy. Okay, but like there's this big gap, and certainly from the standpoint of differential privacy, we want to understand this gap. But another motivation for trying to understand this gap is that this type of attack, so that this style of attack where you kind of determine conclusively who is and isn't out of the data set for every person, is kind of provably like impossible when you go above this error. Right? So we need some sort of new like technique or new story for what type of attack you can pull off. And there's like a very simple kind of argument for why this type of sort of reconstruction guarantee cannot be achieved, which is that I can apply this random sampling argument to the database itself. So if your distribution is now the data set, and you just randomly sample it, you take like m random samples, you'll get accuracy 1 over root m. So if m is like n over 1,000, then you'll get accuracy about 1 over root n. But you will also make it impossible to figure out if 99.9% of the people are in or out of the data set. Everyone who wasn't sampled is just like a random person from the population. Adam looks slightly unhappy. Very happy? Okay, good. We're in Paris, who could not be happy? Just sorry, I have to write it down in the Adams. I have to write down the Adams retirement party notebook. Okay, he'll yell at me later. Okay, so let me tell you. So we needed a new attack to get around this kind of subsampling issue. Like we need to sort of relax what type of attack we can try to carry out, so that we can get these optimal lower bounds. And we did this in sort of like two kind of separate works that I'm glomming together into one talk. So in the first work with Mark Bunn and Salil Vadan, we basically got a lower bound for differential privacy. So we got something that's sort of not really an attack, but we were able to show that no differentially private algorithm can output even like a minimally accurate answers for these marginals when the dimension is bigger than n squared. Yeah, I'm like swapping notation a bit, but if you look at the bound we had of root d over n, like that bound goes to garbage exactly when d is n squared. You can get the right sort of trade-off in between. Okay, and the proof involved this connection with a really cool kind of information-theoretic object called a fingerprinting code, which was just invented by Bonnet and Shaw for a totally unrelated problem in watermarking. And there's like a truly beautiful construction of Tardos. And no, sorry. So like the bound was like we had like root d, Jesus Christ, root d over n. So right, this becomes like 1. Okay, good. So this is good. This establishes the lower bound we want in differential privacy. It closes this gap for differential privacy. But because we were sort of using this like kind of very brittle construction of fingerprinting codes, it requires like a very strong adversary. Like the attack works in a very worst case model where we control the data and we control the adversary's knowledge. And differential privacy says that we shouldn't even allow attacks in those settings. But maybe realistically you could ask like, is this plausible? And just to prove like that this is a very sort of like complex and brittle thing, back in like 2003 when Adam read this paper, he thought, he's not Hungarian enough to solve this problem. Fortunately, I'm half Hungarian on my mother's side, so I'm happy to translate for all of you. This is what Adam looked like in 2003.
Not mine, but yes. Is that also
That's Adam's. No, that's Adam's. I'm very disgruntled face. He finds this paper very inscrutable. Okay, so what we did is we sort of went into the guts of this fingerprinting code, and we sort of showed that basically like the methods in this fingerprinting code's paper actually give attacks that work under fairly plausible assumptions. So let me describe this theorem, which is from a paper with Cynthia and Adam, as well as Thomas Steinke and Salil Vadan. Let me start by saying what the conclusion is. So we don't get this kind of strong guarantee that I can take any individual's data and figure out if they are or not in the data set. That's inherent. What we prove is that I can figure out if there's at least one individual that I can sort of conclusively say is in the data set, and everyone who's not in the data set I'll sort of conclusively say is not in the data set. All right, and then in order to get this, we need more assumptions. So first of all, we need to assume that you get like n squared noisy marginals. Okay, so this is because we have this differentially private algorithm. We need n squared. We also need to assume that the data set, it no longer just comes from sort of any reasonable distribution. It kind of has to come from like the population itself has to be chosen in sort of a nice way. Okay, and I'll describe that and say a little bit at the end about like what nice means. Yeah? I am not. I'm like deliberately like never going to go in. I mean, I'm going to go into the proof. Great. Yes. So the set of colluders is the people in the data set. Okay, the set of people registered in the system is the population, for those who know how this works. I mean, I'm going to go into the proofs. I'm just not, I'm going to like drop this fingerprinting code like language. Like I'm never going to use it as a black box. Yeah. Sorry, yes, right. There are some people who consider this just Hungarian enough. Okay, so what are our assumptions? Okay, so we have high dimensional data. And as I said, the data set, like the population itself needs to be chosen in sort of like a nice way, which I'll talk about. We need the data of the target individual, just like this Homer et al. Attack. And another feature of this attack is that we don't need like very much information about the population. Okay, we just need like a single random sample from the population. Okay, so I don't need to know the marginals. I just need like a single sample. All right, so these assumptions. So when I say nice, as I said, be patient. When I say minimal knowledge of the population, we just need this one independent random sample.
What's the comparison between the top and the bottom? Is it a weaker assumption?
Good question. So yeah, so it basically, this is a stronger statement than this. Okay, so differential privacy basically says that I shouldn't be able to tell if you're in the data set or not, even for an adversary who has like arbitrary knowledge of your data and and like arbitrary auxiliary information about the distribution. So here we're saying that, and also it should hold for like every population, right? So differential privacy is like all these strong quantifiers. This is sort of like the negation. It says sort of like there exists a distribution and an adversary who can tell if someone, who can identify someone, and therefore it rules out differential privacy. This sort of says like for most, or for many, many settings, there's a way to tell if someone's in the data set. So it not just rules out differential privacy, it's like a sort of functional attack you could imagine running.
And you still see a range of N and D, right?
And it's still, yeah, so it's exactly the same parameters. Quantitatively, it gives the exact same lower bound. It's just that this is more of like an attack you could execute, and this is like a technical lower bound. Thanks, that's a great question. Okay, so this basically completes the picture. So this gap is now something like constants or log factors, but the point is that basically in every sort of parameter regime at a coarse level, we can, there's this threshold. Either you can get differential privacy by this very simple, efficient algorithm, or a somewhat plausible attack applies. And I'll say at the end a little bit about like what I mean like plausible. Okay, good. So I have I think enough time to give you like the high level. Sort of a high-level description of the attack. Yeah, thank you. So let me, I'm going to take advantage of the board here. I'm going to actually like sort of draw the model for the attack on the board. That way it can like stay up while I'm talking. All right? So my drawing skills are not good. Bear with me. All right, so this is the population. And this is like a product dist on vectors in 0 plus minus 1 to the d. Okay, that's the population. From it, I'm going to get like an n by d data set.
So you're assuming these d attributes are independent?
Yes, yes. So that's going to be crucial. I'll talk about, maybe at the end I'll say a little more, but in some sense this is necessary. I mean, if you knew a priori that all the attributes are the same, then the problem is no harder than releasing one marginal, which we saw is easy to do. So there's a lot of room in between all marginals are the same and completely independent, but some assumption of this sort is necessary. Okay, so we have a data set. It consists of n vectors and plus minus 1 to the d. We have a target individual. Okay, and I'm going to say in a minute where the target individual comes from. And we have this like one reference sample, which is also an element of D, and this also comes from the population. Okay, now what do? We compute some like vector of marginals. Okay, this is like real valued d-dimensional vector. And we have an assumption that the marginals are at least somewhat accurate. So the marginals satisfy that if I take the average of the n people in the data set, then the difference between m and the correct marginal is maybe like 1/10, or 1/10 is somewhat arbitrary. So this is what I'm calling accuracy. All right, and now we're going to feed all of this into an algorithm called the tracer. Not really important what it's called. And it's going to output like one of two things. It's going to output either that the target individual is in the data set or out of the data set. And in is supposed to correspond to the case where this target is like a random sample from the data set. And out is supposed to correspond to the case where the target is a random sample from the population independent of the data set. Okay, so this is like our attack model. This is a good time to, ask questions, criticize my drawing skills, whatever you want.
So the reference sample is just 1 point?
So for now the reference sample is going to be just a single sample. So like the, sort of the least non-zero amount of side information you could have about this population.
So does the tracer use the reference sample? It's like not connected to anything.
Yep. Nope. Criticism. I said criticism of drawing skills is fair game. Yes, the tracer uses the reference sample.
The reference sample is not the same as getting the population marginal.
Correct, right. So it's like think of it as like an unbiased estimate of the population marginals. So essentially, like what we're going to do is we're going to show that, like, even if there's a high variance but like unbiased sample, it's enough. All right. So now that we have the attack model in place, I can tell you like what the actual attack is, like what the tracer is. Oh, I guess as you'll see in a minute. So the tracer is labeled A for attack. Okay, and like the tracing algorithm, the attack is like extremely simple. Right? Like it's this is the entire algorithm. And what does it do? So it basically says, look, like I've got this target. Right? I've got this guy and his data. And I've got these marginals. And I have something that I know is like independent of these marginals. I know that it has like the same mean, but is like independent. So what it's going to do is it's going to say how correlated is the target with the marginals. That's this term, y comma inner product of y and m. And it's going to say, all right, how correlated is this independent sample z with the marginals? Okay, and this is like a calibration. Like if the population, only output the vector +1, +1, +1, +1, then like, of course, like this independent sample will be like very correlated with the marginals. This is like some way of sort of calibrating what is like the baseline correlation that the population enforces. Okay, and then all it's going to do is it's going to do like a significance test. It's going to say like, if the correlation between the target individual's data and the marginals is significantly larger than the correlation between a random person and the marginals, where this value is the significance threshold, although it's not super important. I mean, it's important, but it's not like, conceptually important. Right, then it's going to say, okay, if it's significantly more correlated, then I'm going to output, yes, this is a person in the data set. Otherwise, I'm going to output, no, this person is probably not in the data set. Yes?
Is this just a two-sample test? So you have two samples for a distribution. You want to know, is it from P or is it from D, which is like a,
Okay, so,
it seems like
okay, so,
a statistics problem.
okay, almost. Let me say, so I'll say just slightly more about this, but let me say that basically, suppose these marginals were like exactly the marginals of this data set, then this is like an exact, like classic, like two-sample hypothesis problem. This is just like, I either got a random draw from this or a random draw from this, and I want to know which one.
But there's just some uncertainty.
The problem is, right, so this is not a single distribution, right? This is like, this is like, there's some algorithm that produces these marginals subject to this accuracy constraint, but there's like many possible distributions on M.
Well, so you have a composite hypothesis on one side and
Okay.
a single hypothesis on the other. So I just
Okay, so then probably,
what would the hypothesis tester decision be?
no.
It's not
Composite on both sides.
Composite on both sides.
Well, it will be.
Because you don't know P.
You don't know P. Yes, sorry, you don't know P.
Okay.
Yes, that's important. Yes, sorry, that's important. You don't know P.
In fact, the Sankararam et al. Paper formulated this explicitly as a
Yeah.
hypothesis testing problem. When P is known or fixed,
Right, that
then
is one
it's,
reject versus the composite.
then it's
Yeah, exactly. So,
it's
right.
actually with exact statistics, it's actually you really both hypotheses are simple, and in that case, you can give the optimal test as a likelihood ratio test,
Right.
and that's what they give.
And in particular, it's like not this test. Like this is not an optimal test. The point of this test is that it's robust to like not knowing exactly what like hypotheses you're testing. This will explicitly appear on a slide later.
I
Okay.
was wondering what it might say for like this test might say for this general hypothesis testing problem also.
It may, I mean, yeah. So
Yes,
this is why we're all together in this room, right? At least you and me and Adam. So okay, so this is our test. It's very simple. Like I can describe like literally the whole algorithm. Let me like give you sort of like some kind of like highlights of the analysis, which are not quite as simple. And also let me sort of just state precisely like what the guarantees are. So the guarantee, like the first claim, is that if this target really is like blue, like if it really came from the population, then the probability that I say in, like the probability I give the wrong thing, is at most delta. Okay, so this is like what crypto people would call soundness. Like the probability of like falsely accusing a person of being in the data set is like delta. The guarantee, however, is like asymmetrical. So you can phrase it two ways. You can either say that if I draw a random person from this data set, then the probability that I say in is at least 1 in n. Okay, so it's not like yes, I say yes. It's not like guaranteed I say yes. Or you can phrase it as like there exists at least one person in this data set for which I will say in with probability close to 1. Okay, so there's at least like some person in this data set whose sort of privacy is really being violated. Okay. Great. So that's the test, and let me give you like just like a little like quick taste of how the proof works. So the first claim is that if you're out of the data set, then I have like very high confidence that I will say you are out of the data set. All right, and like this is sort of the simpler directions. Like why is this true? So like fix any answers. Like I don't even care if they're accurate. I don't care anything. Just like fix any vector m over here. And now like take two independent draws y and z. Because if you're in this blue case, then like these are just two independent draws from the same distribution. So the expected value of this inner product is just 0. Like it's just inner.
What do you mean by you're outside the data set? Isn't it like a property testing type thing where you actually have to be far from the data set?
Well, no. So it's not like when I say out of the data set, I just mean like you are a random person in this population. Okay, so like for all we know so far, the population could be like supported on like one vector. Okay, so the point is not really like distance from the data set, it's just like independence from the data set. Right? So like the marginals, if you look at this diagram, are like independent of the target if the target is sampled this way.
So when you say target is out, is that with high probability over y drawn randomly from the population?
Well, this is just an expectation. Right? This is just saying that like get rid of this red line, then like this vector, and now fix this vector, then like this is one independent draw from a distribution, and this is another independent draw from the same distribution.
So I guess my question is, the one you mean by y is out, is the setting where y is...
No, okay, so y is out is not like a definitive like thing, right? Y is out just means that I sampled y randomly from P. It's possible that there is a person in this data set who actually has the same data as y. I'm talking about like the sampling procedure, not the data itself.
So soundness is almost the average case rather than this case?
Well, no. So it's actually very worst case in the sense that like it is true that like if it's the case that like this population is like supported on a single vector, then we'll just say everyone is out. So like soundness will always hold. Like soundness is very worst case. The assumptions are going to come into the like completeness half of the claim. Okay. So this is clear now. So it's just saying that if I'm in this case where y is sampled from the population, then all I'm doing is I'm looking at like two samples from the same distribution, and their correlation with a fixed vector has zero mean. Okay. And so not only does it have zero mean, but if I assume that this is a product distribution, then it's like the sum of a bunch of random variables that are bounded between -1 and 1. So using something like Hofting bound or Chernoff or favorite theorem, you can prove that the probability that the inner product exceeds this threshold is at most delta. Okay. All right. So soundness, like very simple. So we don't falsely accuse people. You can set delta to be like very small. So if we say you're in the data set, like you better be in the data set. All right, so now here's sort of the trickier part, and I'm only going to be able to give like a very quick kind of like sketch of what we do. So this is the part that says like there is at least one person in this data set where if we sample that person, then the probability that the tracer says in will be like close to 1, like fairly high. All right, so let me I pretty much want to avoid like the sort of actual theorem. I want to basically just give you some intuition for like the simplest possible case, which is really like the previous case of Homer et al., where everything's fixed. So let's suppose first of all that the dimension is 1. Like let's just start by fixing like one marginal, because everything's independent. We're just going to study one marginal, and everything is going to follow by like linearity of expectation and independence. And then like simplification 2, let's like forget this accuracy for a second and just assume that you tell me the exact marginal. So you tell me the exact average of all the bits in this one column. And let's also like even simplify things further and just assume that the population is like uniform. Okay, so like I literally just have a data set which is just one column of like n independent coin flips. Okay, so like why will this thing be large? Well, we can just calculate it. Okay, so like fix any person in the data set, right? Fix like any person in this data set, and you can like literally just calculate the expectation of this quantity. And I won't go into it, but if you expand it out, basically like, right, this is xi's data, this is the average of everyone's data. One of these terms is xi. Every other term is independent, so the mean goes away. And you get that the expected value of this product is 1 over n. Okay, so like all this says is if I take a vector of n random bits, and then I fix like a coordinate, then the correlation between like that coordinate and the average is 1 over n. Like a very like simple statement.
What happened to Z and M?
Oh, so z is just like another independent bit, and so like the expected value is 0. So z like the
Okay,
yeah.
but M was fixed.
Sorry, there's like two. No, so m is not fixed. M is like specifically this
Yeah,
vector,
that's right.
but it's like independent of z. Okay, sorry, so I combined like 2 steps until. Okay, so now like you just get that for each marginal, you have correlation 1 over n. And so by linearity of expectation, if you take d marginals, the correlation becomes d over n. And because they're independent, it's very concentrated around d over n. And so you can just ask, like, when is d over n bigger than this threshold? And it's when d is like n squared. Okay. And in this special case, you can get a tighter analysis, which is how you get the stronger theorem Dinner-Nissim, but like this is enough for us. So to go back to Anand's question, this is sort of like a simple kind of hypothesis testing setting where we say that if you're out of the data set, then your distribution is like binomial with some mean and some variance. And if you're in the data set, then the distribution is like some different binomial that's been shifted, but with the same variance. And in this setting, there's like an exact, you can just say exactly what the optimal test is if you want like kind of false alarm probability delta and misdetection. Hopefully using those terms right.
Well, so I guess the question is, is there any benefit to like doing a name-and-Pearson type thing where you fix the false alarm and optimize them all?
Well, okay, so I mean, first of all, like our model we sort of want deliberately to have like delta be the kind of false alarm probability. Like that's sort of like an external.
Delta on both sides, actually. Right?
Yes, well, in this case, we'll get delta on both sides.
So you're operating in this sort of
I mean, it's
point of the false
yes, we're fixing a point, but yes, the point is that these are two fixed distributions. So like Neyman-Pearson like applies. There's like an optimal test, and it's like maybe in this very very simple case this is the test, but in general this is like if you allow like the bits to be non-uniform or something, this is not the optimal test. But what's nice about this test is that it's like very robust to like having like different distributions. Basically, when we start allowing for like different populations and different assumptions and different accuracy, like this sort of out case will stay this kind of nice thing, but the in case will sort of become like some weird distribution. Yes, Al?
I'd argue that the real difficulty, well, the difficulty comes from the variation of the population, like you were saying.
Yeah.
But
also the accuracy.
Well, it's the fact that you don't know the mechanism.
Right. Well, but I'm saying even in the simple case where the mechanism is like release exact marginals, then you're still in the
LR test is essentially
yeah.
the same.
Okay. It's
the form
it's the same form with a different threshold, I guess.
too much, right?
Okay. I mean,
the threshold will depend on the marginals.
the threshold will depend on the marginals. Yeah. But the point is that we're going to be in a very general setting where there's no like Neyman-Pearson optimal test. And so we're trying to sort of approximate it. But like a great question for like information theorists is like, what is the optimal thing to do here? Like we have a more general problem, but there's still some like optimal thing. It may not have the like strong optimality properties of like the Neyman-Pearson tests, but like there's something optimal. Maybe not universally optimal. All right, so let me just give like a super, super quick like sketch of how we get a statement for like sort of arbitrary noisy marginals. So like what are the problems? Like suppose we're still going to simplify with d equals 1, but like what are the problems that come up? So like we already said that like noisy answers are sort of non-reconstructible. Like we're not going to be able to get some sort of guarantee about every target because there might be some targets that are like independent of the marginals. Okay, so like the example here is like you take the average of like n over 1,000 random subsamples. And so what we do is we don't argue that the correlation between like a fixed target and the marginals is large. We argue that like the correlation like on average, like if you sum the correlation over all of the targets, the correlation is large on average, and so there's some person with high correlation. All right, and then like the second thing is that if the population is like fixed, so like if we're in the setting where I fix that the population is uniform, so like I fix that all I'm getting is a vector of like individual random bits, and now I allow you to give me an answer with error larger than 1 over square root n, here's like a really trivial algorithm, like output 0. Right? Like, I mean, by concentration, like this is a pretty good mechanism. Like the answer will be plus minus 1 over root n. So output 0 is fairly accurate. And so what we need to do is we need to assume that like the population marginals themselves have a lot of uncertainty. So like what we're going to do is we're going to add like a distribution over populations. And this is going to itself be like a nice product distribution on like the marginals of the population. Okay, so like in the d equals 1 setting, what we're going to do is we're going to like draw a random number p between like -1 and 1, like say even uniformly. And then we're going to sample the population will now be like every person is independent with bias like p. Okay, and this basically means that like there's no mechanism that just ignores its data. Like you have to look at the data in order to figure out the marginal, because if you just answer some fixed number, like you're not going to get a good estimate. And then like what we prove is this thing that I'm calling like the fingerprinting lemma to tie it back to sort of the like fingerprinting codes of Tardosh, which is like basically just a nice sort of encapsulation of his analysis. And what it says is basically like, if you draw a random marginal p for the population, and then you like sample people from that population independently, then like one of two things is large. So either like the expected correlation is large. This is like 2 slides from now. Like either the expected correlation is large, or there's like a lot of error between like the marginal, like the population marginal and the data set. Okay, so we say one of those two things is large, and then like playing around with this, you sort of get that someone has to be. Okay, it's a little technical. I can like describe it a little more offline. It's not super hard. So let me like, I'm going to say nothing about the proof. We can prove it like 3 ways, but I'll show you none of them. So what I want to do is basically just put up this landscape. So like I want to summarize the talk by saying that we now know for this like simple problem of releasing the marginals of a data set in a high-dimensional data set, we have like an almost like complete sort of characterization of like when privacy, or at least when differential privacy is achievable. And I also think that the lower bounds like are now established by a sort of realistic attack. So if you're interested in like different definitions of privacy, I think this like attack is sort of realistic enough that you should think about whether it's plausible in kind of your model, right? And if it's not, you're making some assumptions, and you should think about like, are those assumptions plausible? Right? Nice. Awesome. Conclusions. There. Conclusion. Animation. I just want to say like, there's many open questions, and I'd be happy to like talk to you guys over coffee about them, but I won't like philosophize about them now. So thank you very much, guys.